Go back and look at this vibrating membrane problem again. We already did it once, but we kind of skipped some steps. Remember, it's a vibrating drum connected at the outside here. U, the function is the vertical displacement. Anyway, here was the partial differential equation. When we broke it down, we got these two ordinary differential equations, one in T for time and one in R. Now, we back when we first did it, we said, let's just only look at the positive lambda cases. Now, you could have said, kind of with some hand waving, that, well, we expected something of a vibrational nature, so that over time you'd expect oscillation. And if you look at the possible solutions to this equation, the T equation, the only one that gives you that kind of oscillation are the positive lambdas. You could say that's why we did it. But let me be a little bit more rigorous about that. Let me skip ahead quite a bit. Let's get back to Bessel functions and Bessel equations and modified Bessel equations and modified Bessel functions. Here was the here is the Bessel equation for integers. Here is its general solution. Here's what Bessel equations of the first and second kind look like. Here is a modified Bessel equation. Again, for integers. It's a linear combination of modified Bessel functions of the first and second kind, and here's what those functions look like. Okay. Now let's look at the equations we had. Especially the R equation. In fact, just the R equation. So here's the R equation, and it had a boundary condition. Out at the edge, it's 0. So when lambda is less than 0, here's the equation. You multiply it through by R, you would see that it is a modified Bessel equation of order 0. Here it is. If n equals 0, you've just got minus alpha squared x squared y, and which is what we have here. R plays the role of little x, big R plays the role of y. So this is a modified Bessel equation of order 0. Here's its general solution. Require boundedness. And the critical point here is at R equals 0. Modified Bessel functions of the first kind are okay. Modified Bessel functions of the second kind blow up as the argument goes to 0. So we set this to 0. Here's our surviving function, the boundedness. Now we look at this boundary condition. At C, we're plugging in C for R. So we have this. We have a C times alpha. Both C and alpha are not 0. So this is some positive constant here. And let's look at that. Oops, well, I sub 0 is never 0 at all. Certainly not for positive arguments. That means we have to set A to 0 to make this true, which would give us a trivial solution. So we reject this whole case. Reject the lambda less than 0 case. Now let's look at the lambda equals 0. Lambda equals 0. This is our equation. Use our formula sheet that has this general solution. Boundedness says at R equals 0, this thing blows up, so we had to set e to 0, so r is just a constant. And if the other boundary condition, this thing's out at the edge is 0, that means a equals 0, we reject it as well. Now we have a more rigorous way, rigorous justification for rejecting non-positive eigenvalues, other than just you expect oscillation. We'll do some more problems in a bit here where we use these modified Bessel. Don't always reject them. So we're going to get into a little bit more of using those modified Bessel.